Good morning, everybody. My name is Ferhan Mazher, and today is 8th December 2020. The day is Tuesday, and right now I am with the 10 Cambridge class, and the subject we are studying is Physics 5054. And today, our main task is because we have completed the chapter of sound. Today's task is to do MCQs which are related with the chapter of sound. So let's start the worksheet, which is on your screen right now. This worksheet is, I have taken it from the website savemyexam.co.uk. So this is the courtesy of that website. Okay, so this is the second session on this worksheet. I have already done one session with the boys section, and we have done the first question till the 21st question. And with you, I'm going to start from the 22nd question. I hope that you will be able to understand this. So let's start. Sound travels at different speeds in air, water, and steel. For these materials, which row is correct? Remember one thing, that the sound, it's the behavior of the sound with regard to its speed is different from the behavior of the light. The speed of the sound will be fastest in solids, and the speed of the sound will be slowest in the gases. The speed of the sound is fastest in solids, and it travels slowest in the air. So what is the choice? On your
A.
screen, you have the sound travels slowest in air and sound travels fastest in steel. So A looks the right answer. A is the right answer. For question number 22, the right answer is A. Do you understand, everybody?
Yes, sir.
Okay, so we are moving to the next question. On your screen, question number 23. Waveforms are shown on a cathode ray oscilloscope for a flute and for a guitar, each playing the same note. The oscilloscope settings are the same for both waves. What is the difference between the two sounds? Okay, so it's this question. It looks very easy, but it's tricky. This is the mean position of the wave. This is the mean position of this wave. This is the mean position of this wave. This is the mean position of this wave. If you look at carefully, we can check from the CRO. The CRO makes a displacement time graph. It always shows you a displacement time graph. So check what is the time period for this wave. This you can count 1, 2, 3, 4, and 5. So this wave is completed in 5 squares on the x-axis. This wave, the first wave, the flute one, 1, 2, 3, 4, 5. So it took 5 squares on the x-axis to complete that wave. So let's see how many squares this wave took. Look at this wave carefully. Just take 1, 2, 3, 4. 1, 2, 3, 4. It takes 4 squares to complete this wave. Okay, and how many here? 1, 2, 3. 1, 2, 3, and 4. This also took 4. I counted 5. 1, 2, 3, 4. This one take 4 squares. This one take 4 squares. So basically their time period is same. Both waves has the same time period. If they have the same time period, they have the same frequency. So both these waves, the flute and the guitar wave, they both have the same time period, and they both if the time period is same, it means that their frequency is also same, because the frequency is equals to 1 by t. So if the time period is same, the frequency is same. And now check, let's check what is the amplitude. Amplitude of this wave is 1, 2, 3, 3 point something. Its amplitude is on the y-axis. We check. Amplitude means how high this thing went. How high this thing went up, or you can say from the mean position how low it went. So the amplitude is from the mean position how high you go, or from the mean position how low you go. So from the mean position it is 1, 2, 3, 3.8 something. Okay, let's check this. What is its amplitude? 1, 2, 3, and 3.8, 3.7. So it appears, it looks that the both have the same amplitude. Both the waves have the same time period, which means they both have the same frequency. Both the waves have the same amplitude, which means they both have the same loudness. His question is, what is the difference between the two sounds? The difference between the two sounds, if you look at them carefully, you will see that their basic shape of the wave, is different from each other. If the basic shape of the wave is different from each other, we call it quality. They have the same amplitude, that's not different. They have the same frequency, that's not different. They have the same time period, that's not different. The quality is different. Quality is basically the basic shape of the wave. That is different, definitely. That's profoundly clear that the basic shape of these waves is different from each other. So the quality is definitely different. The D option is the wavelength. From, remember, this wavelength thing, we cannot find out the wavelength from this graph. The graph which is produced of a sound wave by a CRO, cathode ray oscilloscope, that graph is basically a displacement time graph. From the displacement time graph, I can find out the time period, I can find out by the formula, I can find out the frequency, I can find out the amplitude, but I cannot tell anything about the wavelength. So the wavelength thing is not clear. Okay, that's I cannot find out the wavelength from this graph. So D cannot be the option. So the only difference between these two waves is the basic shape of these waves, which means the quality is different. And we call this timbre. Do you understand?
Yes, sir.
So what's the choice?
C, sir.
E is the right choice. C is the right choice. The difference between these two waves is quality. Okay, on your screen, question number 24. A flash of lightning and the corresponding sound of thunder are detected 6 seconds apart. A student calculates that the lightning struck about 1800 meters away. On which assumption is the calculation based? Um, you know, the assumption which we make in these experiments when we calculate the speed of the sound, we assume one thing. The experiments in which we have a flash of light and we are at a distance from the flash of light, and when we hear the thunder or we hear the bang of that flash, one assumption which we have made is that the light is traveling very fast, but the sound is traveling relatively very slow as compared to light. In these experiments, we assume that the light will reach you immediately, but the sound will take some distance to reach you. Okay? So the basic assumption in these experiments is whenever a thunder happens, or whenever a flash gun is fired, or whenever an explosion takes place, the light will reach you immediately because the light is traveling very fast. But the sound is traveling very slow as compared to the light. So that's our assumption. Light, the options given are, can you choose the right answer? Can you choose the right answer? Hello? Hello? Can you choose the right answer? Are you able to hear me? On which assumption is the calculation based? A option is the light reaches us almost instantaneously, but sound travels at 300 meters per second. That can be the right answer. Light travels 300 meters per second faster than the sound. No, no. The difference is too very large, not this one number. Light travels 300 times faster than sound. I don't know. We can check this thing. The sound of the thunder was emitted 6 seconds after the flash. That's totally wrong. So the basic assumption which can be correct is, let me this first one. Let me check the speed also. Let me put it here. Okay, so I can find out the speed of the sound. The speed is equals to distance divided by time. So they said that the distance covered by the sound was coming from 800 meters away, and if I divide it with the time taken is 6. So my final answer will be something 300 meter per second. So A looks the best answer. Light reaches us almost instantaneously, but sound travels at 300 meter per second. So to me, it looks A is the right answer. Do you understand?
Yes, sir.
Okay. So A is the right answer. I hope you have understood this. Okay. So we are moving to the next question. This is question number 25. During a thunderstorm, there is an interval of 1.70 seconds between an observer seeing the lightning and hearing the thunder. The speed of the sound is 340 meters per second. What is the distance between the observer and the storm? You see, it's a very simple distance time question. The thunder happened at some distance and we want to calculate it. So we know that the distance is equals to speed multiply time. And the speed of the sound is already given to us. The speed of the sound is 340 meters per second. If you multiply it with the time taken, that is 1.70 seconds. So do you have the calculators with you? Do you have calculators?
It's 578 meters, sir.
578 is the answer. 578 meter is the answer. If you multiply 340 with 1.70, you will get the answer 578 meter. So the choice is C. I hope that you have understood this numerical.
Yes, sir.
Okay, very good. So let's move to the next question. The next question is question number 26. An ultrasonic tape measure is used to find the distance to a wall. It sends out an ultrasonic pulse and times how long it takes for the reflected pulse to return from the wall. The ultrasound has a frequency, a wavelength, and a speed. Which pair of values is needed to find the distance to the wall? We need to find out if you are using that thing. Basically, I need to know two things. I need to know what is the speed of the pulse, speed of the ultrasound in the air. And the second thing I need to know is that how much time the ultrasound took from your instrument to go to the wall and come back. Okay. So basically, this is that you have an ultrasound machine in your hand, and you send a pulse. The pulse goes out, the sound waves goes out, and it is reflected from the wall, and it comes back. So your machine should know two things. One, it should know the speed of the sound, And the second thing it should note down is how much time the sound wave took from going to from machine to go to the wall and come back to the machine. If you know these two things, the time and the speed of the pulse, then you can simply multiply the time with the speed, and whatever the distance you get, you divide it with 2, and you will get the distance between you and the wall. So look at the options. Frequency and the wavelength, frequency and time taken for the pulse to return, speed and time taken for the pulse to return, wavelength and time taken for the pulse to return. So what is the best option?
C.
C is the right answer. We should know the speed of the ultrasound, and we should know how much time this ultrasound took for going to the wall and coming back. Then you can calculate the distance between you and the wall. So C is the best option, sir. You understand? Hello, do you understand?
Yes, sir.
Okay. So that was question number 26. C was the option. Okay. On your screen, question number 27. The diagram shows the trace produced on a cathode ray oscilloscope CRO by a sound. Which trace is produced when both the loudness and the pitch of the sound are increased? Look at here carefully. He's using a few words. He's saying he's going to increase the loudness and the pitch. The loudness depends upon the amplitude. So let's first of all concentrate on loudness. The loudness depends upon the amplitude. This original sound, this is the mean position of that sound, and this is 1 square going up. That amplitude is 1 square. It means from one step it goes up, or you can say it's 1 step it goes down. The amplitude is 1. So if the loudness is to be increased, then whatever is the right answer, its amplitude should be more than 1. From the mean position, it should go more than 1 square upward, or from the mean position, it should go more than 1 square downward. Okay, the second thing he is saying is pitch. The pitch depends upon the frequency. So if you will increase the pitch, he said increase the pitch. If you will increase the pitch on the same display, now more number of waves will be shown. On the original display, there is 1 complete wave only. When you will increase the pitch, which means you will increase the frequency, so on the same display of the CRO, now more number of complete waves should be shown. So the correct option will be that which have a higher amplitude and which is showing more number of waves in the same display. So what is the choice? What is the choice?
D.
What you said?
D, sir.
D is the right answer, ma'am. D is, yes, Amna, D is the right answer. D is the right answer. Everybody understand this thing? Do you understand this thing?
Yes, sir.
Okay. So the next question. Question number 28 is on your screen. Delicate instruments are often placed in a box to protect them from stray magnetic fields. What is the material used for the box and why is it chosen? This question is not from the sound, but anyway, we can answer. This question is from the magnetic, chapter magnetism. That box, which if we have delicate instruments and you want to keep them safe from the stray magnetic fields, and we always put them in a box of soft iron. We always put them in the box of soft iron, so no magnetic lines from anywhere else can reach them. This is called magnetic shielding, or we also call it magnetic screening. So D is the right answer, but this MCQ which is showing on the screen is not from the sound. So D is the right answer. Okay, this one is very important. It's very, very, very important numerical. The girl standing 150 meters in front of a tall building fires a shot using a starting pistol. A boy standing 150 meters from the girl hears two bangs 1 second apart. From this information, what is the speed of the sound? Okay, let me copy this from here and we take this thing into the paint and I can explain you there. Okay. Let me take it to the paint. Okay, so here we have. So you can see this girl fired a pistol, a shotgun. So basically, what will happen? Sound waves are produced and they will spread in all directions. This girl will produce a sound, and that sound will travel in all directions. And one sound wave from this will travel directly to this boy. And check this sound wave, which has traveled directly to this boy. It has covered how much distance? It has covered 350 meters. So the sound wave which is coming directly from the pistol to the boy, it has covered 350 meters. Another sound wave will go towards the building. It has covered 150 meters in going to the building, and then it will come back to the girl 150 meters back, and then it will travel 350 meters further to the boy. So this sound wave, it has traveled how much? This blue color sound wave, which went first to the building, got reflected from the building and traveled back to the boy. So let's see how much distance this sound wave has traveled. 150 in going to the building, 150 coming back to the girl, that's 300, plus 350 meters from girl to the boy. So this blue sound wave which I try to represent, it has basically covered 650 meters. It has traveled 650 meters. You understand? So one sound wave went directly from the pistol to the boy, and that sound wave covered 350 meters. Another sound wave from the pistol first went to the building. From building it got reflected, came back to where the girl was, and then it went to the boy. So the distance traveled by this reflected sound wave from the building is 150 going to the building, 150 coming back to the girl, and 350 going to the boy. So the total distance traveled by this blue colored wave is 650. So the difference of distance between these two sound waves is 650 minus 350. So the difference is how much? The difference is 650 minus, let me change the color. So 650 minus 350. So the difference of distance traveled is 300. The distance traveled by both the sound waves, the difference between the distance traveled is 300 meters. And the boy heard the original sound and the echo 1 second apart. The time lapse was 1 second. If the time lapse is 1 second, so the time difference, the time taken for this difference of distance is 1 second. So divide it with 1 second. So 1 second. So you will get the speed of the sound. The speed of the sound will be 300 meters per second. It's a tricky one. Do you understand? So the final answer will be 300 meters per second. Do we have that choice? The choice is A. Do you understand?
Yes, sir.
It is a tricky one. This is a question numerical related with the echo. Question related with the reflected sound waves. I hope that this is clear to you. It's the peak of its concept, okay? Okay, the question number 30 on your screen. Let me reduce the size. Okay. A boy strikes a rigid metal fence with the stick to create a sound along the fence. A girl listens with her ear against the fence. 1 second after the fence is struck, the girl hears a sound through the air. How long it takes for the sound to reach the girl through the fence? Okay, you see, the boy, it's just a metallic fence, and the boy struck it with the stick. So the sound will be produced. Now the sound will reach the girl by two mediums. The sound will reach the ear of the girl through the metal fence, and the sound will reach the girl's ear through the air. Through the metal fence, the sound travels very fast. It is something like 5,000 meters per second. This is just for knowledge, for your knowledge. The sound travels like 5,000 meters per second in a metal. But through the air, the speed of the sound will be only 300 meters per second. So through the metal fence, the sound will reach the girl very quickly. He said she heard the sound through the air after 1 second. So through the fence, she will hear the sound very, very quickly. The time will be less than 1 second. It's a purely conceptual question. The time should be less than 1 second. How long will it take the sound to reach the girl through the fence? Through the air, it took 1 second. So through the fence, because in the fence, the sound will be traveling very, very fast. So it should take less than 1 second. So what's the choice?
B.
B is the right choice. Do you understand this idea? It's a conceptual question. A very conceptual question. Do you understand? Yes, sir. Amna said yes, sir. Okay, shabash. Let's go to the next question. Okay, on your screen, we have question number 31. The diagram shows oscilloscope traces of sound picked up by microphones. The oscilloscope controls are set in the same position for all the traces. Which trace shows the sound that is both loud and low pitched? You see, low pitch means less frequency. So low pitch means less number of waves on the display. Okay. less number of waves on the display. Another way of finding that is that on the x-axis the time period for a complete wave. For which shows the sound that is both loud. To be loud, the amplitude should be larger. Let me take this diagram to the paint so we can work on it. Okay, let me take this. New one. I'll bring on this here and then we will be able to work on it actually. So okay, let me copy it from here. Let me take it in the paint and then I can work on it. Okay, so here we go. So check the let's say first check the amplitude. This is the mean position. 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 I'm marking the mean position. You can see on the screen. Yeah? I am right now marking the mean position with the red. Okay. So with the blue, I'm going to mark the amplitude. The loudness depends upon the amplitude from the mean position, how high you went. The amplitude of this is 2 point something. So it's loud. Its amplitude is 1. Its amplitude is 2 point something. So A and C has the same loudness. Its amplitude is only 1 square. So amplitude is from mean position, how high you went. And loudness depends upon the amplitude. So he said, which sound is more louder? So it can be A or it can be C because they have higher amplitudes. The second thing is, which has the question, let me change the color. Okay, that's color. Oh, okay, green color. Okay. So his question was low pitched, which has the less frequency. Low pitch. Let's check what is the time period for this wave. The time period is, okay, count how many? 1, 2, 3, 4, 5, 6, 7, 8. Its time period is approximately 8 squares. So check what is the time period for this wave. 1, 2, 3, 4, 5, 6. Its time period is 6 squares on the x-axis. Its time period is 8. I'm not talking about the frequency. I'm talking about the time period. We are supposed to find out which is most loudest and which has the low pitch, loud and low pitch. A and C has more loudness than B and D. So B and D are discarded. Now the competition between A and C. A and C both have the same amplitude, so their loudness is same. Now I'm looking for low pitch, less frequency. Because this is a display of a CRO, from its x-axis I can find out the time period. A's time period is 8 squares on the x-axis to complete a wave. And C, it has 6 squares. So which means its time period is approximately 6, let's say. And you know the frequency is the reciprocal of the time period. F is equals to 1 by T. We know that. F is equals to 1 by T. We know that. F is equals to, F is equals to 1 divided by T. So who will have the less frequency? 100% this one. This will have the less frequency. So A will be the choice. Look at the question again. He says, which trace shows the sound that is both loud and low pitch? So A is the right answer. You see, It's not that easy to answer it. We have to from the given diagrams, I have to very carefully decide which has more loudness and which is low pitched. So A is the right answer. Do you understand? Do you understand this whole discussion?
Yes, sir.
Yes, sir.
Okay. 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 Shabash. So that was question number 31. Okay, on your screen we have right now question number 32. The graph shows at one instant the pressure variation along a sound wave. So this is a diagram. Basically, this is a graph. And the graph is between pressure and the distance. So on the y-axis, the pressure is represented. And on the x-axis, the distance is represented. And if you remember, if the distance is given on the x-axis, we can find out the wavelength of the wave. If the distance is represented on the x-axis, we can find out the wavelength of the wave. And because on the y-axis, the pressure is represented, and they are talking about a sound wave. The point where the pressure is maximum, that point corresponds to the compression. And the point where the pressure is lowest, that point corresponds to rarefaction. So this pressure distance graph, from the x-axis, I will be able to tell you the wavelength, and from the pressure y-axis, I will be able to tell you where there is compression and where there is rarefaction. Wherever the pressure is maximum, highest value of the pressure, that represents a compression. Wherever the value of the pressure is lowest, that is representing a rarefaction. So which point on the diagram represents a rarefaction, and what is the wavelength of the sound wave? The wavelength of the sound wave, this is representing nothing, and this is basically representing wavelength. So X is representing basically the wavelength, and rarefaction is at the point Q, because the pressure is minimum. The pressure is on the y-axis. So this point has the minimum value on the y-axis. It's in negative. It means less than the atmospheric pressure. So it is the lowest. Y is representing nothing here. It's not amplitude. Don't confuse it with the amplitude. Amplitude can be, somebody asked me, Amna asked me, that what the Y is representing. The Y, if it is a displacement distance graph, if it is a displacement time graph, then that Y thing will be the amplitude. But right now you can say it's just telling you what is the from the mean position, from the atmospheric pressure, how high is the pressure in the compression. So forget Y. Okay. So the rarefaction is at point Q, and the X is representing the wavelength. So the choice is C. Everybody understand this?
Yes, sir.
Do you understand this?
Yes, sir.
Question number 33 is on your screen. The diagram, let me increase the size. Can be more clear. The diagram shows a loudspeaker that is producing a continuous sound wave of frequency 200 hertz in air. 200 hertz in air. Which diagram best shows the sound causes a molecule at P to move during 1 by 200 second? 1 by 200 second. Okay. So, which diagram best shows how the sound causes a molecule at P to move during? So, we are talking about a sound wave. And here we have the loudspeaker. And the sound waves are going towards right. So from sound waves are going from the left to the right. And we know that the sound waves are longitudinal waves. So when the sound waves travel, the particles of the medium vibrate parallel to the sound wave. If this particle is representing a particle of air, particle of medium, because the sound waves are going towards right, this particle will be vibrating parallel to the direction of the sound wave. The sound wave is going towards right. This particle should move, vibrate parallel to the direction of the wave. This is the basic characteristic of the longitudinal wave. The particle of the medium vibrate parallel to the propagation of the wave. So the P should be vibrating. It should go to the right, then should come back to the left. Right, left, about its mean position. It will vibrate. It will go to the right, it will come back to the left. Yes, A is the right answer. A is the right answer. If the sound waves are going towards right, the particle of the medium will be vibrating parallel to the direction of the wave. They will be also vibrating about their mean position, forward and backward, left and then back, and then to the right, and then forward, backward, left, right. They will be vibrating parallel to the direction of the sound. So A is the choice. Do you understand?
Doctor.
Dua, do you understand?
Yes, sir.
Okay. It's a longitudinal wave. So A is the choice. Question number 34 is on your screen. Which of the following does not produce a sound wave? Which of the following does not produce a sound wave? A bell ringing under the water. It will produce a sound wave. A gun fired in a room with no echoes. It will produce a sound wave. A hammer hitting a block of rubber. It will produce a sound wave. An explosion in the outer space. It will not produce a sound wave because the sound wave need a medium. And in the space we have vacuum. And the sound wave can only travel through a medium. When there is vacuum, there is no medium. So the sound wave cannot be produced. So what's the choice?
D.
D is the choice. Okay, D. So by this, we have reached the end of this. This worksheet has 34 MCQs. With you, I have done from question number 22 to 34. And the time of our lesson is also about to finish. This was an MCQ worksheet on the topic of the sound. This worksheet I have taken from the website savemyexam.co.uk. So I hope that these questions which we have done today are helpful to you. So thank you very much, everybody, and have a good day, and God bless.